Hello friends, today we'll see about the fundamentals of metal casting. So in this particular lecture, we are going to see about overview of the casting technology, heating and pouring, and solidification and cooling. So we are now dealing with the casting process. So what is meant by solidification process? Solidification means conversion of liquid into solid. So the starting material in this particular process is either liquid or is in a highly plastic condition, and a part is created through solidification of the material, that is from liquid to solid phase. Solidification processes are classified according to engineering materials, processes such as metals, ceramics, or specifically glasses, polymers and polymer matrix composites. So in this particular chart, you can see the classification of soliding processes. First comes the casting of metals, which again is further divided into expendable mold casting and permanent mold casting. And again in expendable mold casting, you have sand casting and other casting processes, which we are going to see in the further coming part. Second one is the glass working, and third goes to the processing of polymers and PMCs, which includes extrusion and related processes, injection molding, other molding processes, and special processes for PMCs. Now, coming to the casting. So casting is a process in which the molten metal flows by gravity or other force into the mold, where it solidifies in the shape of the mold cavity. What is the shape of the mold cavity? Accordingly, you will get the casting. If it is a rectangular, you will get a rectangular. If it is a circular, you can get a circular one. So what is the shape of the mold cavity? You will find that particular shape of the casting. The term casting also applies to the part made in the process. So the steps in the casting seems to be very simple, which includes melt the metal, pour the metal into the mold in which the casting is produced, and let that particular melt gets freezed. So what are the advantages of the casting? Which you can create the complex part geometries, you can create external and internal shapes. Some casting processes are net shape, others are near net shape one, can produce very large parts, or some casting methods are suited to mass production. So these are some capabilities and advantages of the casting. So you can produce complex parts, some external internal shapes, some mass production parts, large parts, net shape and near shape parts. Again, the disadvantage associated with the castings, there are limitations of the mechanical properties, poor dimensional accuracy and surface finish for some processes, for example sand casting, because there are the possibilities of sand getting being washed, or sand being mold being gets broken, so you will have a very poor dimensional accuracy or surface finish, but you can do the casting with the help of sand also. Safety hazards to the workers due to hot molten metal, because the melting temperature or the molten temperature range is ranging from some 1300 to 1500 degrees Celsius. So which can have the require safety hazard to the workers, and also it creates a lot of environmental problems such as smoke, dust and all these things. But these are the disadvantages of casting processes. So the big parts which are made by the casting process includes engine blocks and heads for automotive vehicles, wood burning stoves, machine frames, railways, pipes, some bells, big statues, pump housings, or you can also produce small parts such as jewelry parts, small statues, frying pans, dental crowns. So all varieties of metal can be cast, ferrous and also non-ferrous. So casting is usually performed in the shop which is called as the foundry shop. So the foundry is a factory equipped for making the molds, melting and handling molten metal, performing the casting process and cleaning the finished casting. This is what is called as the foundry shop. Workers who perform castings are called foundrymen. Now, what is mold? Mold in the casting. So, it is a cavity whose geometry determines the shape of the part. So, actual size and the shape of the cavity must be slightly oversized to allow for shrinkage of the metal during solidification and cooling. What is the meaning of this? So, if you make a shape exactly to the casting shape, then what happens? The metal have the tendency to get shrink or freeze. So, in that case, you don't have the exact shape of the casting which you require to be produced. For this purpose, the actual and the shape of the cavity must be slightly oversized to compensate for the shrinkage effect. So molds are made up of variety of materials which include sand, you can make a plaster molds or ceramic and metal molds also. So here in front of you, you can find the two types of the molds. The first part, that is A, which is shown over here, it is called as the open mold, that is which is open to the atmosphere, simply a container in the shape of desired part. So this you can say this is the mold, and this is the cast metal you have to pour in this case. And the second part, it is called as the closed mold, in which the mold geometry is more complex and requires some type of the system which is known as the gating system, where you can find there is a pouring cup through which the molten metal is poured, and now this vertical part is called as the downsprue, through which the metal comes here, and this horizontal part this horizontal part is called as the runner, through which the metal runs, and through particular area which are called as the gates, which enters into the mold cavity, and here you will find the cast material and some metal which is come up in the mold, which is called as the riser. And here you can see there are two parts, one is called as the cope part and another is called as the drag part. Here in this case you will find there is a single container, but here you can find the two parts. One is the upper part which is called as the cope part, and another is called as the drag part. Drag means the bottom part of the mold and cope is the upper half of the mold, and they are bolted together with the help of some nut and bolts, and the line which is separating cope and mold, it is called as the parting line, where you can have there are two parts of the mold. Upper half is called as the cope and the lower half is called as the drag one. So two categories of the casting processes which you have seen earlier, that is expendable mold process, means where you can use the mold which must be destroyed after removing the casting. That means uses an expendable mold which must be destroyed to remove the casting. So mold is destroyed here, so you have to make the new one. So mold materials you can have sand, plaster, or you can use the binders also. And the permanent mold process means you can use that particular mold over and over again for many castings. So these are generally made up of the metals, because metals will run for a long time. So expendable molds are the molds which you can destroy after removing the casting, and the permanent mold processes is you can use that particular mold for over and over again. So you can have more intricate geometries here. Part shapes in the permanent mold processes are limited by need to open the mold. Permanent mold processes are more economic in high production operations. So where you can have the high production rates, you can go for the permanent mold casting. So this is the sand casting mold which you have seen here earlier. Again, I am going to give you the description over here. You can see this part will constitute as a gating system, and this is called as the sand casting mold. And this is nothing but the sand which is rammed around that particular uh, pattern or the uh, casting process. And these are the things which you have explained to earlier. This is the pouring cup through which the metal is poured in this particular mold, which comes through down sprue and runs through the runner and enter into the mold cavity, and after solidification we will find the casting. So sand casting mold terms, that means mold consists of two halves. One is called as the cope, upper half of the mold. This is called as the cope part, which is the upper half of the mold, and this is the lower half of the mold, which is called as the drag. So mold halves are contained in the box called as the flask. So this is a particular flask through which these two mold halves are there, and two halves are separate by a parting line. So this is the line which separates scope and drag mold. How to form the mold cavity now? The mold cavity is formed by packing sand around a pattern. Pattern is what? Pattern is nothing but the replica of the casting. What is the shape of the casting required from which you are making the casting? That particular basic material is known as the pattern, which is nothing but the replica of the casting. So you have to pack the sand around the pattern, and once you pack around the sand, then the pattern is removed and the remaining cavity of the packed sand has desired shape of the cast part. That means if you want to make such type of the casting, then you have the same shape of the pattern, and through around this pattern the sand is rammed very packly, and after that this pattern is removed so that you can have that particular cavity of the shape of the pattern inside the mold. So when the pattern is removed, the remaining cavity of the packed sand has desired shape of the cast part. The pattern is usually oversized. Again, what I'm saying, listen carefully. The pattern is generally made oversized because metal have the tendency to shrink after when it is getting solidified. So to compensate for that particular shrinkage, the pattern is generally made oversized so that after pouring the metal, when metal starts contracting or solidifying, then it will come to the shape of the exact shape of the casting. Sand for the mold is moist and contains a binder to maintain the shape. So sand is nothing but it contains certain ingredients. That means it contains some amount of water, some amount of binders, so that it will provide the strength to the sand so that it can stick to the pattern, and when you remove the pattern it will not fall. So it is called as the green compression strength. So some binders are added to improve the binding capacity so that sand can stick to that particular pattern and which will not get removed after removing the pattern. So to provide a particular strength, binders are added to the sand. Now what is meant by core? Core is nothing but when you need to provide certain hollow shape inside the casting, then one process is to machine so that you can have, or drilling so that you can have that particular hole in the casting. But every time if you go for doing this, it will take a lot of long time. Instead of that, a core of that particular diameter is kept inside the casting so that inside the mold, so that when you pour the metal, the core automatically gets burnt out and that particular hollow shape will be created in the casting. So the mold cavity provides the external surface of the cast. In addition, casting may have internal surface determined by the core placed inside the mold cavity to define the interior geometry of the part so that it can produce. Generally, when you require a hole in the casting, you can go for the cores. And these cores are generally made up of sand, different types of sands. Getting system, once again I am coming to that. The channel through which the molten metal flows cavity from the outside of the mold consists of the downscrew through which the metal enters the runner leading to the mold cavity. Once again I am telling, this is a pouring cup through which the metal is poured inside, and through which this is the vertical channel through which the metal comes inside the mold. This vertical channel is called as the downscrew, and this is the horizontal channel through which the metal runs, and that is called as the runner. And this is the particular cast metal in the cavity. So this is what is comprises the gating system of the casting. At the top of the downscrew, a pouring cup is often used to minimize the splash and turbulence as the metal flows into the downscrew. Because what happens when you pour the metal, there the metal has a tendency that it will splash out from this particular splash out. So to prevent the splash, if you don't have that this shape, so if you make the shape equal to this, the metal will splash out. So to avoid that splashing, this shape is made some wider so that metal will freely enter into the downscrew. And the riser is nothing but the reservoir of the mold in which the source of the liquid metal to compensate for shrinkage of the part during solidification. What is the meaning of riser? So this is a riser This is the last part to solidify. Once the metal enters this particular cavity, the section which are very thin, that in that particular thin shape, the metal gets solidified quickly. But as the uh, casting dimension, it is not of a same dimension. Somewhere it is thick, somewhere it is thin. The thin part gets solidified first and the thick parts get solidified later. So the metal have the tendency to solidify as long when it comes in contact with the mold. So the thinner part gets solidified easily, but thicker parts, it will take some time for the thicker part to solidify. So in case if there is a shortage of metal, so that the thicker parts does not get solidified quickly as or equally with respect to the thin section, then there is a problem of shrinkage, or somewhat we can call it as the unfilled mold. So to compensate that one particular liquid, that liquid is supplied by this particular riser. So because when there is a shortage of the metal, then this particular section will get the metal from this particular riser, which will fulfill the requirement of the metal. So that's why riser is there, which is called as the reservoir of the metal, which will provide the metal as and when there is a shortage of the metal. Now, how to make the metal, heating the metal? So some furnaces are there which are called as the, you can have induction furnace, cupola, where you will use the scrap or the raw material to heat the metal to convert them from solid to liquid stage, or you can metal to the molten temperature. So once the heat required is the sum of heat to raise the temperature of the melting point, heat of fusion, and heat to raise the molten metal to desired temperature for the pouring. So when you use the furnace, when you start the furnace, first what it will do, it will raise the temperature so that that particular part or the particular material inside the furnace starts heating up, and they will get converted into liquid. And once it reaches to the melting point, the particular melt has been prepared, and once that melt is prepared, again it is heated so that it should have that mold running capacity. So to molten metal is again heated to the particular range or somewhat to the higher temperature, so that it can sustain its temperature. So once the metal is ready, that metal, particular metal is that particular metal is poured into the mold cavity. So the factors which determine the success is the pouring temperature. What should be the temperature during pouring? What should be the rate of pouring? And whether it has providing any turbulence or not. So pouring temperature means, suppose you prepare a cast iron melt. So cast iron, you will have a melting temperature around 1000 to 1100 degrees Celsius, but that temperature is not sufficient to pour. Again you have to some provide certain amount of it so that its temperature rises. So when you start pouring, it should be poured at around 1300 degrees Celsius, 1300 to 1400 degrees Celsius, and with the controlled rate, so that it should not happen like if you are pouring 10 molds, so you should pour in the proper way so that all the 10 molds get filled in particular time without any turbulence in that particular process. So how the metal solidifies? So there are two solidification, solidification depending whether the metal is pure metal or an alloy metal. So here in front of you, you are having a cooling curve for the pure metal. So here in the pure metal, this pure metal solidifies at the constant temperature. That is the most important parameter. A pure metal solidifies at the constant temperature equal to its freezing point. That means same as the melting point. So here you can see this is the pouring temperature. So when you pour that particular metal in the pouring cup, that is called as the pouring temperature. And once you pour the metal, it will come through the downsprue. That means it will start coming, or this is called as the liquid cooling. In this particular range, the metal is in the liquid form, and here it will start freezing. That means it solidification starts and it will go for some constant temperature, and again from this again it starts freezing. That means here freezing gets completed and solid cooling will start. So this is the cooling curve for the pure metal. This is the pouring temperature. This line indicates the liquid cooling, And again here in this particular, that's why it is called as the constant temperature. That means local solidification will start, and this in local solidification, from this freezing begins and here freezing gets ended, and from here the metal will again start cooling. This is called as the solid cooling, this is liquid cooling, and this is local solidification time. And from this particular point to this particular point, this is called as the total solidification time, the total solidification time required for that cooling the casting. So but this is not the ideal scenario. What happens in this case, when we pour the metal immediately will come to this particular, it will cool suddenly below this particular line, below this particular line, and at this particular, now see this arrow, this will not end. This is the ideal curve, this is the ideal curve, but every time our metal will not cool like this is the ideal curve, but metal will suddenly cool and come down below this freezing point up to here, and then it will stop its freezing again. That means here temperature goes on decreasing up to this level, and again at this particular point it starts raising, and now here from here it will start freezing. So that is called as the actual cooling curve for the pure metal. This is the ideal cooling curve, and here metal will not freeze exactly at this point but below this point, and this is called as the undercooling process. That is called as the undercooling process, where this is the ideal. Here it will freeze. That means you can ideally picturize like this. It will come here, it will freeze, the freezing begins, then freezing ends, and this. But this is not the actual case. Suddenly it will go down below this freezing, and after certain amount of time again the temperature starts rising, and this will come from this particular to this area, and now freezing will begin. So this particular portion which comes down, this is known as the undercooling. So undercooling is very necessary for particular solidification process. Without undercooling, solidification will not start. And now this is this particular, from this to this is called this is the area which is called as the overheating, and this is the undercooling. Okay, understood this? Now what happens actually when you pour the, suppose this is the mold. Now consider this is the mold, and uh, this is the casting where that is you are this is the particular mold, this is the sand over here. Okay, now when the metal comes here, from the metal having the temperature around the range of 1400 1500 degrees Celsius, and now this particular mold is at the room temperature. This is at the room temperature, and the metal has a high temperature around 1400 degrees Celsius. So when the metal is poured in this particular mold, what happens? This particular area which is at the room temperature, the metal when it touches over, suddenly this part will get the chilling effect. This part gets chilling effect, and suddenly there is a solidification starts from this particular area, and you will find such type of grain structures here in particular this particular area. These particular areas which you are seeing in the white, they will freeze immediately, which will create chilling effect, and this you will find the grain structure of the casting of the pure metal. So this is called as the, these grains are called as the equiaxial grains. These are called as the equiaxial grains. So once the metal will come from this to this, from this to this, what will happen? Now solidification, due to it metal gives latent heat of fusion. So again here the temperature goes on increasing, temperature goes on increasing, and the grain structure will be like this. Now this will start growing in this direction. Here you will find equiaxial, some circular types of grains, and here you will find the long type of grains. These are called as the columnar grains. These are called as the columnar grains, and these are called the equiaxial grains. This happens due to immediate chilling of the, this immediate chilling, that immediate solidification of the metal, chilling effect happens, and the grain structure of that particular becomes like this. These are called as equiax, and after this again the temperature rises and it will be in this direction or in this direction or in this direction. These are called as columnar grains. This is the called as the solidification of the pure metal. That is due to chilling action of the mold, a thin skin of the solid metal is formed at the interface immediately after pouring. So skin thickness increases to form a shell around the molten metal as solidification progresses. Rate of freezing depends on the heat transfer into the mold as well as the thermal properties of the metal. Again, latent heat of fusion and all these things will come into the picture. So the metal will start losing the heat. Again, its temperature goes on increasing and the grain structure will change from equiax to the columnar grains. This is the case of pure metals. But alloys will not solidify as like the pure metals. They will freeze over the temperature range than a single temperature. They have more than one temperature. That's why the cooling curve for this particular alloy is like this. If you see the cooling curve of the pure metal, you will find after this liquid cooling, it will have a horizontal line parallel to the time axis or x axis. But this is not the case in with alloys because they will not freeze at the single temperature. They will freeze over the range of temperature. That's why the cooling curve for the alloy is like this. Okay, so that is the difference between the solidification of pure metal and alloys, because solid pure metals will freeze at a single temperature and alloys will freeze over the range of the temperature. So the characteristic grain structure, if you find here for the pure metals, you will find here some chilling effect here, and the grain structure is here like this. But in case of the alloys, you will find chilling effect like this. Again there is a columnar grains, again there are equiaxial. So it is a mixture of equiaxial and columnar grain structures. So to find out the solidification time, so what is the solidification time? The time from pouring to the end of the solidification is called as the solidification time. So solidification time, TS, TST, what is, or T you can say, solidification time. So it depends upon the size and shape of the casting, and which is given by one rule by a person called Chorino's rules, which states that TST or the solidification time is equal to Cm into bracket V by A raised to n, where TST stands for the total solidification time. So total solidification time is given by Cm. Cm is the mode constant, V is the volume of the casting, and A is the surface area of the casting, and n is the exponent. This n is exponent, but generally it is taken as 2 every time, and Cm is the mode constant. From with this formula, you can able to find solidification time of that particular casting. What is the solidification time required? What casting is given by Chorino's rule. So the mold constant Cm, it depends upon what kind of mold material you are using and what are the thermal properties of the castings and what is the pouring temperature. From this you can find out the mold constant, that is mold material, thermal properties and pouring temperature. So the value of Cm for a given casting operation can be based on the experimental data from the previous operations. So you can have that previous data so that you can have that particular Cm value with you. So what does the Chorno's rule tells? That a casting with the higher volume to surface area ratio cools and solidifies more slowly than one with the low ratio. If the V by A, volume upon area ratio is higher, V by A is higher, then solidification is very slow. On the other hand, if V by A area is less, then solidification will be faster. So to feed the molten metal to the main cavity, so TST for riser must be greater than TST for the main casting. That means this is most important parameter, that is TST stands for solidification time. So the riser should solidify after solidifying the casting. That is the most important parameter you have to take into consideration. The riser is the last point of solidification. So the solidification time for the riser must be greater than solidification time of the main casting. If riser solidifies first than the casting, then the casting will not get sufficient amount of liquid for the feeding. That's why the solidification time for the riser must be greater than solidification time of the main casting. Since the mold constant of riser and casting will be equal, design the riser to have larger volume to area ratio so that the main casting solidifies first. This is another rule which Chornos tells us that mold constant of riser and casting will be equal. So you have to design a riser to larger volume upon surface area so that the main casting will solidify first. So this will minimize the effect of shrinkage. So what is the meaning of shrinkage? Shrinkage means there is a shortage of metal. Suppose now shrinkage of a cylindrical casting during solidification. This picture shows that here starting level of immediately when you pour the casting, that means when you fill the mold, the initial level will be like this. Okay, it is exactly at the top of this. The metal is exactly on the top. So as the time passes, what will happen if you find here from this to here, the metal will start reduction in the level. See here. So initial level. So what will happen when this mold metal will touch this surface? What will happen? It shows the chilling effect. So chilling effect means this part of the metal gets solidified quickly because it is at the room temperature and the pouring temperature is higher. So this pouring metal temperature is higher and this mold is at the room temperature. So there is a difference in the temperature range. That's why what happens when it touches the mold wall, this particular metal solidifies immediately. That's why the level of this particular metal will be like there is a reduction in the level, right? Because you see over here, this part gets solidified immediately, right? Now, what happens next? Here, reduction in the height and the formation of the shrinkage cavity caused by solidification shrinkage. Again, if you find as the metal goes on cooling from here to here center, that what I have shown you, chilling effect and then columnar and dendrite grains, the level of this particular reduction in the height due to solidification shrinkage, this level goes down and finally you will find solid thermal contraction over here. Okay, this is the molten metal. It goes on here from this point to this point, it starts solidifying like this. So again, height will go on reducing, and after certain period of time, the metal this gets solidified now. Okay, the only part remaining is this the molten metal, and once gets this is you will find this particular shrinkage cavity. There is a shortage of the metal, solid thermal contraction happens. For that, risers are to be used. So solidification shrinkage means which occurs nearly all metals because the solid phase has higher density than the liquid phase. The solidification causes reduction in the volume, and so exception is cast iron with the high carbon content. So carbon content is high. There is an exception in this case. So graphitization during final stage of freezing causes expansion that counteracts the volumetric decrease. So this is one case with the case of cast iron. So for compensate for this, the pattern makers account for the solidification shrinkage and thermal contraction by making the mold cavity oversized. That's why the mold cavities are made oversized to compensate for the shrinkage allowance. Okay, that is the reason why the patterns or the molds, why they are made up of oversized to counteract for the shrinkage allowance. Now, how the casting solidifies? There are two ways of solidifying. One is called as the directional solidification. The directional solidification means this solidification starts from thinner section and ends in the riser. That is called as the directional solidification. So to minimize the damaging effect of shrinkage, it is desirable the region of the casting most distant from the liquid metal supply to freeze first for solidification to progress from this remote area towards the riser. Okay, so the solidification should start from the farthest region from the liquid metal supply to freeze first, and then it progresses towards the riser. Thus, molten metal is continually available from riser to prevent the shrinkage. So, if the casting, the part which is away from the riser should solidify first, and from that particular point, it will end in the riser so that it will provide a proper uh, solidification process and it will not create any shrinkage defects. The term directional solidification describes this aspect of freezing and methods by which it is the controlled solidification. So how to achieve this solidification? So desired direction solidification is achieved using Chernov's rules to design casting itself. That means you have to locate the sections of the casting with lower volume upon area ratio away from the riser. That's why I told you the areas which are away from the riser should freeze first, so that they should have V by A ratio. Considering V by A ratio, then those regions should solidify first and then it will come towards the riser. Or you can use the chills. Chills means these are certain heat, internal external heat sinks that cause rapid freezing in certain regions of the casting. Suppose some areas are thinner and some areas are thicker. So thinner area gets freeze first, but the thicker areas will take more time than the thinner area. So if you want to freeze those thicker areas equal to thinner areas, you should place certain external heat sinks. Those are called as chills, so that they are equally solidified with respect to thinner sections. So that is the use of chills. So these are the chills. So this is the external chill and this is the internal chill. So this junction, if you find external chill to encourage rapid in. Now this area, this is more thicker section. So this, so to freeze this, you can use these particular chills, so that freezing will rapid freezing will takes place, or you can place inside also, so that this particular area gets freeze as fast as the thinner sections. And the last point of this is the riser design. The riser, as I told you, is the reservoir of the metal, and it will provide the necessary amount of metal whenever there is a shortage of metal. A riser is a waste metal that is separated from the casting and remelted to make more castings. To minimize waste in the unit operation, it is desirable for the volume of metal in the riser to be minimum. Since the geometry of riser is normally selected to maximize the V by A ratio, this allows riser volume to be reduced to the minimum possible value. So we will discuss this riser design and the type, what are the different riser design methods. We will discuss in the next lectures. For that particular region, this what we have seen earlier, we have just discussed about what is meant of casting and how the casting is produced, what is the mold and what is the how the metals are melted, and how the solidification plays important role in making the casting, what is the Chernov's rule, what is the effect of this, all we have discussed in this particular lesson. And in this next part we will discuss about riser, what is riser, what are the riser design methods, and how those particular methods are used for designing the risers. For now, thank you very much. Thanks.